Welcome everyone. I see everyone has their video already off. I appreciate, but well, after during discussion you can switch on if you wish. Well, my name is Jose Antolinez. I am assistant professor in the coastal engineering section at TU Delft, but I'm also coordinating the AI working group of DigiShape, and this is one of our technical sessions of DigiShape, and today we have with us Thomas Stolp from HKV that is going to talk about spatio-temporal prediction of bed levels. So maybe Thomas, I give you the floor first. Maybe the scheme will be Thomas will present, and then we have room for discussion for any question you have. So Thomas, whenever you are ready, please go ahead.
Yeah, thanks. Yes, thanks for the introduction. So today I want to talk about a topic that I've been working on, more or less for over 2 years already, and not the whole time, but it's something that we try to keep progressing and developing, and that's the bed level prediction on the Waal using spatial-temporal networks. So that's I'm gonna explain it in a bit, but basically come down to using the full resolution data as it's also measured. So grid data that has a time dimension as well. And I'm gonna first introduce a bit. It's gonna be a technical session. I'm gonna go into the model challenges that we kind of face in applying these networks to this application. And later I'm gonna talk about some data pre-processing that we improved actually. A student that I supervised for the last couple of months did quite some good work there. And after that, there's room for a discussion. I'm also curious if you guys work on this topic or what you think about model selection, the approach, or application. So how we came about is in June 2022, a colleague of mine, Andries, and also Joost, they got DigiShape money for doing some research project on the question of can we predict bed levels in the Waal with machine learning. And I came in the picture a little bit later, and when we developed like the first model, that aims to do that. And later on, I also, as I said, supervise a student. We also published an NCR poster, and now we're at that's actually done, and we are looking for the way forward, I think. And let's see. So in the Waal River, bed levels are actually measured like bi-weekly for actually a long period. And we are also involved in a digital twin of the Waal, where we put all these data together and also visualize it. And I also like to watch these videos where you really see dunes of migrating along the river. You can also see there at least you can track dunes, and there seems to be patterns emerging, maybe predictable. I'm not gonna go into full detail of how you actually apply. So we are focusing on forecasting of dunes or undepths in the river, and that may have all sorts of applications. And but today I'm gonna focus on the challenges that we face around forecasting, making predictive models. So I actually work quite a bit with such AI models. I do it for solar radiation. It's based on satellite images of clouds. We try to make nowcasting or short-term forecasting of how clouds move, and based on that we can also with another model we can turn that into incoming solar radiation for net congestion, also in the Netherlands, a big problem. And another application we use it for is extreme precipitation events. And there are different models that can handle these grid structured data that is also temporal. And one of them is, for example, generative serial networks. And one model that we have a bit more experience with, and that we know at least we know it works good, and we also use it in various research with students, is the trajectory GRU model. And the research question that we try to tackle is it possible to train such a model for predicting bed levels at the Waal River? And first, I'm gonna look a bit more into the data itself. And this is one section of the Waal that we used for a case study. And you can see that there is around every 14 days, we get new measurements, multi-beam echo sounder measurements, actually for the entire Waal. It's actually quite a large data set from 2006 until now. They are measuring it. And it has a high resolution spatial, 1 meter. Temporal, it's a bit more coarse. And as I said, in this DigiShape seed money project, we used a model that we know quite good, and that we know that can with relatively easy make predictions and learn kind of these progressions. And the model is called GRU, we call it. It's a paper from 2017, and it's an improvement of an earlier model, and it uses an encoder-decoder structure, so convolutional layers, pooling, and these recurrent cells, and they kind of use earlier frames and kind of learn a state from that, and they give it to the next one. And a certain amount of frames you can use as inputs. That's variable. I guess in the paper they used 6 or something. And you can also choose how many frames you want to predict in the future or ahead. And that's in these recurrent cells for grid data, they actually used also convolutions in there. So normally in time series models, you kind of lose the positions of cells, but with convolutional LSTMs, for example, or the trajectory GRU, these actually also contain convolutional layers. So the kind of 3D structures of these tensors, they stay the same. And the nice thing about trajectory GRU is it actually adds another function where it can learn to sample from earlier frames where to look. And that's also if you have like rotating structures, and you can imagine in clouds or in weather events, those are they just appear in your input data, and it's more flexible in that sense to learn these patterns instead of in normal convolutional LSTMs where you always have the same neighborhood in your previous states. And that's why it's pretty powerful. And we actually, I modified it a bit so that it's more simple. So 2 frames go in. I think I also shrink it a bit in the amount of layers that are in there, and 1 frame goes out, so that we have a simple model, and we can without going into too complex from the start, I can say okay, is there something, can we train this model, and can it learn the dynamics of the dunes or of the bed levels? And now I want to actually talk about, okay, why is this challenging in this particular case? Because it works quite well for weather events, and those are typically that's typically data that has regular time intervals. So every 5 minutes we get a new radar image, or every 50 minutes there's a new satellite image appearing. And in this data set, it's a bit different. So the data gets measured around every 14 days, but there is spread in there. It can be 10, it can be 20, somewhere in between. And that's actually quite challenging to use this information in such a network. So the first thing I actually did was narrow the training data. So just said from between, I think, 10 or 18 days, we use that data, and then it's more or less in regular time intervals. You can also see here, is actually what we look at with Luc, a student, that there's a spread in discharge as well. And we know from literature that the dunes are kind of really different for different flow regimes. And they also move faster. And that's why we also created a split. Oh, sorry. In training data, so we only look at low discharges. And that's also the most interesting, because then you kind of have in-depths in the river. And another thing that we did is, because we know more or less how fast the dunes move with different discharges, we can also manipulate our data set and then say, okay, if we have irregular time intervals of like 12 days, can we shift the data a bit so that's more or less in line with the 14 days interval? That's what we did for the complete training data set, to improve or to make it a bit easier for the model to learn the dynamics, because that's challenging. That's a bit of a spoiler. Another another improvements we did with Luc, or Luc did actually in his thesis, was to remove outliers from the training data, first of all. And that was something that we did not fully tackle at the first time. And it's always important in these kind of for these kind of models. If you have large outliers in the data, you always get like dampening of your outputs. We also did was, okay, the river has a lot of bends, and we choose on purpose an area or a section that's relatively straight, but that's not always the case. So we use streamlined coordinate transformation to make it more or less, to make it actually exactly straight. And in this way, you can, train your model on one section, but it's kind of the same for the whole river. It makes it easier for training. And what we also did is, the river has, the data is all of these small ripples, and those are actually not really important for the application, because we are only interested in the minste gepelde diepte, the highest point on the bed. And you can say, actually, well, your deep learning model has max pooling layers, has convolutional layers, so it will be kind of reduced, like in training, irregular if you do this, but we choose it at another step to make the training quite easy, a bit more easy. And that's actually, it looks something like this, where it just moves based on a wavelet reconstruction. Wavelet, it actually tries to reconstruct the signal with waves. So looking at the results then, so here you see some results of Luke's thesis. Here it shows first the input cell. So that's like now, you can say, and the other one is 14 days ahead. And that's actually what we tried to reconstruct. And we also did try different loss functions. Root mean square error was the best one. That's with the letter D. And we also put the dots on the highest points in two sections, so the left-hand side and the right-hand side. And you can see that if those kind of match up or not. And what we also notice is that we get smoothed output. That's something that we always kind of see with these models. And there's also some fading, and that is encountered more often. That also, it's a sign that it's still a bit hard for the model to really learn to reconstruct the signal. And I have to say that the amount of frames that we are training on is like in the order of a few hundred. So that's relatively small. If you compare it to data sets that we use for precipitation forecasting, that's actually way more, because we have every 5 minutes we have a new frame, and it has also been collected for over 10 years. So that's really challenging, but still you can see the reconstruction is getting a bit more closer, and it definitely is really improved compared to this model that we have at the start. So that's that gives a bit hope. And let me see if there's, I think this is my I think this is my last slide. So I'm quite interesting if you guys have questions, and if you also what you guys think of this approach, because of course you can say for the applications maybe not necessary to know the whole frame, or you're only maybe interested in the highest points in the riverbed, and maybe that allows for another way of modeling this this problem. But we kind of looked at, okay, taking the most detailed data set that we have, and you can always aggregate after that. Is it possible to use these kind of models for doing that? Okay, so that was my presentation. Do you guys have questions?
Thanks very much, Thomas. And just start asking. If there are many questions, I will moderate. Okay.